This question is from GATE 2022 Mechanical Engineering Paper Set 2, question number 65. Consider a hydrodynamically and thermally fully developed steady fluid flow of 1 kg per second in a uniformly heated pipe with diameter of 0.1 meter and length of 40 meter. A constant heat flux of magnitude 15,000 watt per meter square is imposed on the outer surface of the pipe. The bulk mean temperature of the fluid at the entrance to the pipe is 200 degrees Celsius. The Reynolds number Re of the flow is 85,000 and the Prandtl number Pr of the fluid is 5. The thermal conductivity and specific heat of the fluid are 0.08 watt per meter Kelvin and 2600 joule per kg Kelvin respectively. The correlation, the Nusselt number Nu is equal to 0.023 Reynolds number Re raised to 0.8 into Prandtl number Pr raised to 0.4 is applicable, where Nusselt number is defined on the basis of the pipe diameter. The pipe surface temperature at the exit is dash degrees Celsius. Let's find out. So this is the pipe. We need to find out the wall temperature at exit. So we need to find out the temperature of this wall because we are being asked to find at the exit. This is the exit, this is the inlet. Now we'll find this temperature using the Newton's law of cooling and the heat transfer being equal to Q, which is given as 15,000 watt per meter square, being the heat transfer from this wall to the outer atmosphere, and the outer atmosphere temperature, let it be T exit. So by Newton's law of cooling, we will have this heat transfer Q will be equal to heat transfer coefficient H into delta T. This delta T is nothing but difference between these two temperatures, the temperature of the wall and the exit temperature. So let's substitute this. We have H into T of the wall minus T at exit. Now in here, we have three unknowns, T exit as well as H. All of the values are unknown to us. So first thing, we can find out H by using Nusselt number given, because Nusselt number is nothing but heat transfer coefficient H into diameter of the pipe. We are being given that Nusselt number is defined in terms of pipe diameter. So H into D upon the thermal conductivity K, and from here we can find out H. But we don't know Nusselt number as well directly. Its formula is given to us as 0.023 into Reynolds number raised to 0.8 into Prandtl number raised to 0.4. So let's substitute Reynolds number and Prandtl number given to us, the diameter of the pipe and thermal conductivity given to us. So rearranging this, we will have H will be equal to K by D, which is 0.08 divided by 0.1 into 0.023. Reynolds number is 85,000 to the power 0.8 into Prandtl number is 5 to the power 0.4. So this gives us the value of H as 307.568. Unit will be watt per meter square Kelvin. So we got heat transfer coefficient H. Now we need to find out the exit temperature, because we know the inlet temperature here or the temperature at the entrance. You can find out exit temperature by using energy conservation. So by heat energy conservation, we have the heat transfer that is taking place through the outer surface of the pipe, which is this curved outer surface, is given to us. Amount of heat transferred per unit area is 15,000. So we can find out the total heat that is entering the pipe through the walls, which will be Q into surface area simply. This will be equal to the heat that is transferred through this fluid. So we know that mass flow rate m dot into thermal conductivity C into delta T. Now we see that heat is imparted to the system and therefore exit temperature should be greater than the inlet temperature. So T exit minus T inlet will give us delta T. So substituting all the known values, we need to find out exit temperature here. Rearranging this, we'll get T exit will be equal to Q into surface area. So Q is 15,000. Outer surface area of the cylinder is nothing but pi into D into L. So pi into diameter is 0.1 meter into length is 40 meter divided by m dot C. M dot is given 1 kg per second and C is given 2600 joule per kg Kelvin. So all of the values are in SI unit. We just substitute them as it is. Plus this inlet temperature, so which is given to be 200 degrees Celsius. So 200. This gives us the exit temperature as 272.498. Of course, the temperature value will be degrees Celsius. Now we have T exit, we have H value, we can find the wall temperature by using this equation. So let this be 1. Putting the values of T exit and H in 1, we have Q is equal to H, that is 307.568 into wall temperature is unknown, so minus 272.498. Putting the value of Q and rearranging this will give us wall temperature TW is equal to 15,000 upon 307.568 plus 272.498. This gives us the value of wall temperature as 321.268 degrees Celsius. But we need to round it off to nearest integer. So this will be approximately equal to 321 degrees Celsius. Let's go back and fill in this answer. The pipe surface temperature at exit TW is nothing but 321 degrees Celsius. To learn more about convection, you can refer to the NPTEL video lecture 16, Fundamentals of Convection. This lecture is from the course Heat Transfer. The course is taught by Professor Sunando Dasgupta. He is from Department of Chemical Engineering of IIT Kharagpur. I hope this solution helps you clear your doubt. Thank you.